All right, well, let's talk about how you produce urine and what's the big deal. The first thing you do is filtration, which is a process of diffusion of solutes and plasma into the glomerulus. And keep in mind, all solid material, big, large solid material, is going to just keep going through the glomerulus and get dumped back into the venous system. Whereas anything small or liquidy is going to get filtered through the glomerulus into the rest of the nephron. The next step is going to be reabsorption. That's going to get reabsorbed either back into the bloodstream. Unless we don't want it, then it'll go to waste. And secretion. That's going to be removal of additional wastes that didn't get filtered, and that's going to get dumped into the renals to eventually go out. So urinary excretion kind of equals the glomerulus filtration plus tubule secretion minus the reabsorption, and that's what we're going to be looking at. Really, this is just a fancy way of saying, you know what, urine, what's really urine is that everything goes through the glomerulus, goes through the tubules, and what's taken out is things that have been reabsorbed back into the body. So how filtration occurs is, keep in mind, we have afferent that's going to be coming in through the bloodstream. We're going to have that Bowman's capsules. Here's just sort of side view, but just know that there's a lot of slits in it, and that allows for liquid to kind of come through this way, but solid material will just keep going and eventually go through the afferent arterioles. And we can actually control speed through how we control how much blood comes in through afferent and afferent. If we make this afferent tubule thinner, what will happen is blood will pass through this much, much faster. And if we make this tube, this afferent tube, bigger, it'll make blood go through slower. If things are going through slower, we'll be a lot more efficient with how we screen things. If things are going very quickly, we're going to be less efficient. We're going to just dump that water, everything back into the bloodstream. And we can control these with hormones that we'll talk about later. The things that we're going to filter out is going to be such things like glucose. We're going to dump all of that back into the bloodstream. Amino acids, of course. Urea is going to be a waste product that's going to leave the body. Uric acid, same thing. Creatine, and we'll have two components of creatine, the precursor and the non. We'll have salts. And these ones are really dependent on levels in your body: sodium, chloride, potassium, calcium, a ton of other electrolytes. Areas that, like, let's say you go ahead and have a Gatorade or a soda, there's going to be a lot of sodium and chloride in it because they put a lot of salt in those, so you're going to be excreting those out. If you drink tap water in Arizona, which is fine, it's going to have a lot of calcium in it, so you're probably going to be peeing out some calcium too. And that's going to lead us to kidney stones, which we'll talk about later. Filtration and membrane into the glomerulus. We talked about different types of openings in cells, and we left one and we said, oh, we're going to talk about this one in kidneys, and we'll leave it there, but let's kind of review them and talk about which ones we have. We have the fenestration, and fenestration caused the glomerulus capillaries to be much more permeable than other capillaries. Other capillaries are only going to have a one-cell space, where by having these large slits in our glomerulus, that's what you're looking at here, these black lines are those large slits, we're going to be able to let a lot more stuff pass through into that Bowman's capsule and eventually down the nephron. So that's going to be the fenestrations. Basement membranes, they're going to exclude large molecules such as proteins. So we're going to make sure that blood plasma does have a lot of proteins in it, 7%. And we want to make sure that that gets dumped back into the bloodstream. Proteins in the urine is a really good sign of kidney failure. That's why when you do a urine test, the first thing that they're going to look for is sugar and proteins. And if they find proteins in your urine, that's bad. If they find sugars in your urine, that's bad too. We'll have a filtration of the glomerulus, which is just going to be the glomerulus will take those liquid and now move it through the smaller smaller nephrons and see what we can use and what we can't use. And we're going to use active transport and facilitated diffusion to do that. But let's look at a better picture of these. So we have the filtration slits. They're really big. And you can see some basement membrane. That's the membrane that allows some things to move through. So something, other places would maybe have basement membranes, but really the only place that's going to have these fenestration, it's really only for the kidneys. The glomerulus flow rate, or GFR rate, is something that we monitor in patients, and the average male produces about 180 liters a day, and the average female produces about 150 liters a day. So now clearly, you know, you don't, oh, I hope you know, you don't produce 180 to 150 liters of urine a day. You actually only secrete out 1 to 2 liters a day, assuming you're a good person and you drink a lot of water. So 99% of that material gets reabsorbed back into the bloodstream. So we filter it, we clean it, but you can see a small amount of it's going to have that urea, uric acid, maybe excess electrolytes. And that's going to be what we call the waste, the stuff that we're going to push out. So we can control that flow rate by increasing flow rate would lead to more urine output, of course, and decreasing flow rate would lead to retention of wastes and things like that. So that makes sense. If you increase your filtration rate, you're going to be able to capture more things. You're going to be pushing them out of the body. If we decrease that filtration rate, we're going to retain those things. And we can control glomerulus flow rate by adjusting blood pressure to the glomerulus. So if this is the glomerulus, and remember how we had an afferent tubule and an efferent tubule? We can do that by sort of squeezing on one side and making it so things can go through faster. That's going to increase the glomerulus flow rate. Or we can make this tube wider, and that's going to decrease the flow rate. How I think about this is if you were to wash your car and your car was a little too far from the hose, what you do is you sort of put your thumb at the end of the hose, and doesn't that make it so the liquid squirts out further so you can hit maybe the back end of your car? So that would be like increasing pressure on the afferent areas, and by doing that, that's going to make the liquids go through the kidneys faster. And we're going to have more urine output, or it's going to increase that speed. If we wanted to decrease that pressure, so if you let your thumb off of the hose, that's going to decrease glomerulus flow rate, and that's going to make it so we can sort of inspect that material a little better and stuff like that. But let's talk about the 3 different ways that you can adjust GFR rates. The first one is going to be auto-regulation, and that's just going to be increasing blood pressure, stretches the afferent. Remember how we have an afferent and efferent? Afferent is coming into the nephron. So increasing blood pressure stretches the afferent arterioles. The stretching of that muscle, which is the tunica media, causes the openings of the ionic channel to depolarize and contract, which means squeeze. And that's going to make the blood pressure inside the glomerulus stay sort of constant. Our next one is sympathetic controls of GFR. This is going to be our fight or flight sort of thing, and that's going to be a way to make it so we reduce GFR rates, and we make it so now we can have blood flow go to the heart, brain, and things like that. So we'll even make it so we won't even have a lot of blood going to our kidneys. And then finally, we can have hormonal control. Of course, you know you're going to have to know this one for the exam. So GFR is going to control a cascade of hormones that sort of just change a little bit, eventually to become the active hormone. So we have angiotensinogen, which is hard to say. Remember, it's got the word gen in it, so it's the pre-hormone produced by the liver. And then what happens is it will meet renin in the kidneys when blood pressure is too low and get turned into angiotensin 1. This will float around the bloodstream until it gets to the lungs, and it's going to meet an enzyme called ACE, and that's going to turn angiotensin into an active hormone, and that's going to become angiotensin 2, and this is going to contract the afferent area, and that's going to make it to regulate sodium and water retention by the kidneys. So the way that we're going to retain water and sodium is going to be to speed up the speed that we go through the glomerulus. And by increasing speed, we're not going to be able to have a really good filtration rate, and that's what's going to happen here. We can decrease this by just shutting this hormone off. Here's the big picture. So it's definitely a big picture. So the liver is going to make the precursor. Remember, it's got the gen in it, so this is the inactive form. And when blood pressure drops, your kidney is going to make renin. Renin is going to convert this into the active form, and what it really does is just shave off 10 amino acids from this larger hormone to make it a little smaller. What then's going to happen is this is going to float eventually to the lungs, and in the lungs it's going to get converted by an enzyme called ACE into angiotensin 2, and that's going to have this cascade event with the body. Let's just do the kidney first. It's going to go to the adrenal cortex, and it's going to say salt and water retention, and that's going to elevate the blood pressure. We're also going to go to the heart and do this thing called vasoconstriction, and that's going to make the afferent arterioles sort of constrict too, and that's going to elevate blood pressure. Again, anytime we're squeezing on those tubes, we're going to make blood pressure go a little faster, and we're going to make blood pressure changes. Finally, we're going to go to the hypothalamus and tell your brain, hey, you're thirsty, start drinking water. And by doing that, you're going to add water to your blood, and that's going to go ahead and stop all this process. Because you don't have enough water in your bloodstream, that's why your blood pressure dropped.